Good afternoon, ladies and gentlemen. Welcome to the Associate Professor Lecture of Dr. Martin Vast, organized by the Strategic Program Cancer of the UMC Utrecht. My name is Nico van den Berg. I'm a Professor of Computational Imaging here in the UMC Utrecht, and I'm also a board member of the Strategic Program Cancer. We are organizing these lectures to honor newly appointed associate professors within the Strategic Program Cancer, and give them the opportunity to introduce and present their research to a broad audience. This can be fellow researchers, patients, but also family and friends, of course. And today it's my privilege to introduce to you my colleague physicist, Dr. Martin Vast. Martin Vast studied physics at University of Heidelberg, and from 2010 to 2013 he conducted his PhD studies on new methods for motion management during radiation therapy at the German Cancer Center in Heidelberg. And after postdoc appointments at the Institute of Cancer Research, Royal Marsden Hospital in London, and the Netherlands Cancer Institute, he was appointed as an associate professor at the Department of Radiotherapy of the UMC Utrecht in 2019. Dr. Vast's main research area is the development of MR-guided real-time adaptive radiotherapy, and in 2019 he received this prestigious NVO-VD grant to develop MR-guided real-time adapted lung radiotherapy. Recently, Martin expanded his horizon and started to investigate cancer applications for MR-guided radiotherapy, and in that context, Martin is a co-investigator and work package leader of the Horizon 2020 funded European Stop Storm consortium that investigates cardiac radioablation to treat tachycardia. I'm sure we hear more about it in your lecture. Martin, I would love to hear it. Your title is very nice, brief, easy, adapting RT in a heartbeat. So the floor is yours, Martin. Go ahead.
Thank you, Nico, for this very kind introduction, and thank you all online and on YouTube for joining my lecture today. As Nico mentioned, today I will talk to you about radiotherapy, and specifically about real-time adaptations of radiotherapy. Before I start my presentation, I would like to say a word of acknowledgement. This work is possible because of our funding agency, specifically the Dutch Research Council and also the European Union. Radiotherapy is a really applied form of science, so we also do collaborate very much with industrial partners, and you see the relevant acknowledgements here on the screen. First and foremost, the work that I will present today is also the work of all of my colleagues and students, and I'm very grateful for all their useful energy that they bring into the project and all the enthusiasm that they bring for real-time radiotherapy. So thank you to all of you. To start with the presentation, I would like to zoom in on lung cancer. And lung cancer is really a very huge societal challenge. So if you think about all types of cancer, and that's the graph shown on the left-hand side, and that's for 2020, then lung cancer takes up a significant chunk of that distribution. If you think about the mortality caused by lung cancer, it even has a greater share. So it's not just very frequent, it also frequently leads to death, which is of course something that we want to avoid, and that's why we apply multiple types of treatment. So there's a whole range of cancer therapies available that are applicable to lung cancer. You see some, the most prominent ones shown here. Today I will focus on radiotherapy, and radiotherapy plays a big role. So 50% of all lung cancer patients are treated either fully or partly with radiotherapy. It's usually used in combination also with other modalities, and it does play a big role, so we need to make it better to heal even more patients. What do we do in radiotherapy? First of all, we have to identify the cancer. We have to visualize the cancer on imaging. You see some really nice example images here of lung cancer patients. And what you notice is this heat map, which is overlaid on top of the anatomical image. So this heat map is the dose distribution. That's what we want to create using radiotherapy. And the goal is to apply a lethal amount of dose to the tumor. But of course, there's healthy tissue around the tumor, so that we need to spare. And how do we do that? Well, we have treatment machines called linear accelerators. You see that here on the right-hand side. What we do is we irradiate from multiple directions so that the dose to the healthy tissue is spread out and it's as low as possible. But we do in the center where all the beams overlap achieve a really high dose in the tumor. The challenge, of course, is that the tumor is within the body, so we don't see it by eye. We need imaging modalities to look into the body to precisely target our treatment delivery. And this is basically the type of imaging here that we had to deal with up until now. So this is X-ray guided radiotherapy. You see that these images do show the tumor, they do show the respiratory motion, but they're fairly rough and they're definitely not real-time. So in order to compensate for this lack of real-time information, we need to have quite wide dose distributions. So this heat map that I showed before needs to be bigger than the actual target to make sure that we hit the target. So breathing motion does affect lung tumors very much. Of course, patients continue breathing during treatment. What can we do about this? This is what we could do so far. So in a respiratory sorted image, we can identify the tumor in different phases of the breathing cycle, and that's shown here. What we can also do is we can overlap all these different delineations of the tumor. So that gives you basically the maximum extent of where the tumor could go at any given time. Now we target this entire area. So you see this here in the film. It's quite inefficient. It does make sure that the targeted tumor receives enough dose, but it's also irradiating healthy tissue too much. So we want to go away from this. What we instead want to do is we want to much better align all these different phases of the tumor and then really adaptively track the tumor. So we want to use the treatment beam to follow the tumor and really personalize treatment in this way. What do we need to do this? We need MRI guidance. MRI gives you real-time information of the anatomy of the tumor within the patient, and it requires a completely different type of treatment machine. You need to integrate MRI with the linear accelerator. And you see a schematic sketch here. This really then allows you to follow the see what you treat paradigm, which is really crucial to real-time radiotherapy. This was a long journey to get to this treatment machine. So that's not something that came overnight, but that's something that started more than 20 years ago here at UMC Utrecht. And you see also the investigators at the top that really pushed this development. So it's my honor and privilege to be embedded in this research group to drive this forward, to develop the MR-linac concept to its full potential. So with the MR-linac, it's not just see what you treat, but also to adapt to it. So just seeing it is not enough. That's nice, interesting, but you need to actually adapt to it. And that's where my research in particular comes in. So you see here in this movie loop the lung tumor moving. These are real-time images. You see the green and red contour around the tumor. So that allows us to visualize and follow the tumor now in real time and to really shrink the high dose area in the patient. So to really only focus it on the tumor instead of irradiating healthy tissue. What's the effect of seeing the tumor in real time and acting on it? That's shown here in these graphs. You see at the top a very small hot dose area, so it's really focused on the tumor. In the middle, you see what we have to do before the MR-linac. So we have to go really large, make sure we cover the tumor all the time because we cannot react in real time. The dose differences that you see in the bottom panel, they are really stark, they are really significant. So we need to make sure that with tumor tracking, we really avoid irradiating healthy tissue. And what will this allow us to do if we can do this? It's very simple. It means that we can go from a lot of treatment fractions to much fewer treatment fractions. That's really the goal also in terms of patient experience and in terms of kind of reducing the burden in the healthcare system. We need to go from the situation where patients need to come 10, 12 more times to a situation where they come only a few times. And in the most extreme case, they might even only come a single time. So that's what we call single fraction treatment. And that's what we are now exploring for certain types of lung cancer. This was computer simulations. This all looked really promising and nice. Important is, of course, to build this in real life, to build this on the real treatment machine. So this is why we built multi-leaf collimator tracking. What you see here is basically a real-time control loop. So you have the treatment beam following the target, and in order to do that, we need continuous MRI monitoring. We need to predict the motion. We then need to adapt the multi-leaf collimator, and that adaptation needs to also be enacted on the treatment machine. So this is a loop that continues throughout the treatment. And as you can see, now the irradiation of healthy tissue is really minimized. This was the system that we built to test it. We used a phantom setup. That's something that we do quite frequently in radiotherapy before going to patients. We try it in phantoms that mimic patients. And you see here in the video what our experimental setup is. So we have our phantom, with which we can also measure the dose distribution. We have a target in the phantom, which we can follow with MRI. Yeah, and then we adapt the treatment beam. And this is a real-time experimental setup. So it's not a simulation, but we do this on the real treatment machine. To look at the results of that work, I will show you some more dose distributions. I think you've seen them a few times by now. It's this heat map. We have the central hot zone, the red zone, and that needs to cover the target. If we don't cover the target properly, if the target doesn't reach its prescribed dose, there's a high chance that the tumor will regrow. So it's crucial that here the dashed line, the prescribed dose, is slightly wider than the solid line, which is our actual simulated tumor. This is a static situation. This is the perfect case. Will never happen in real life. Nothing is moving, but this is what we can get to at best. Now, if we don't do tracking, what happens? Of course, the anatomy moves. We are not reacting to it, so we're just ignoring it. You see at the top of the dose distribution, there's quite a bit of dose missing, and that's causing the problem. That's the area where tumor cells do not receive a sufficient lethal dose, so it's much more likely that they will regrow. What do we achieve with tracking? Well, you have to really zoom in on the static versus tracking scenario here to see any differences. So basically, it allows us to completely restore the perfect dose distribution, despite having a lot of motion and also variable motion in this phantom experiment. So this is now showing us in the phantom that we can make the system work. Obviously, the next step is to try this in patients. And this is why we initiated here the Utrecht RT trial. So we are in the preparatory phase for this trial. And with all our technical developments and expertise, we are in a strong position because we can now merge that with our clinical expertise in lung cancer and also with guideline recommendations that we described on an international level. So all this combined will allow us to really bring tumor tracking safely to the patients. And this is, of course, something we desire to do because then we can ultimately prove that this is beneficial for a large patient group. So I think I tried now to convince you that we learned how to deal with respiratory motion, but that's not the end of the story for today. So there's a second chapter, and this is about the heart, and this is about cardiac motion. So cardiac motion is tricky. This is 4 times faster than respiratory motion, typically, in the average human. It's also very localized, so it depends very much on where exactly you are in or close to the heart. So this is relevant actually also can be relevant for cancer patients. So you see here an example of a central lung tumor, and that central lung tumor is right next to the heart. So if the heart beats, it will also displace the tumor during treatment. Cancer is not the only application, though. There is a probably bigger field which is now opening up, and that has to do with a cardiac arrhythmia. So this is something we call ventricular tachycardia. So it basically means the ventricles are beating or pumping too fast. So it's not the regular sinus rhythm anymore, but there's an infarction, a scar in the myocardium, which leads to a rapid contraction. So that's a really unpleasant condition to be in. There's medication available, there's anti-tachycardia pacing available, but it often comes to an invasive catheter ablation procedure as last resort. So this is, if everything else fails, then we need to go invasive. We need to try to locally ablate the source of the ventricular tachycardia. And this is also a really, really big societal challenge. So sudden cardiac death, you can see the incidence here, 50 to 100 per 100,000. So this is affecting a lot of people, and ventricular tachycardia together with ventricular fibrillation are actually the 2 main contributing factors here. So there is a huge need to improve therapy options also for these patients. And the invasive catheter ablation does not always work. It's sometimes impossible to reach the location that needs to be ablated. It sometimes just recurs after a couple of months. So we need new treatment options. And this is where radiotherapy comes in. So a couple of years ago, in 2017, there was a breakthrough from this group in St. Louis in the US, where they demonstrated a workflow on a conventional linac where they could target very precisely parts of the left ventricle, guided also by electrophysiological information, and then ablate this using radiotherapy. So this is a non-invasive new treatment option for this patient group. Does it work? That's a crucial question. This is the graph I want to show you on this question. So if you see here on the left-hand side, that's the number of VT episodes these patients experience per month. And each of these episodes is really, extremely unpleasant experience, of course. Once you have the treatment, there's a few weeks that go past for the treatment effect to establish, and then basically the number of VT episodes goes right down to 0. And that's, of course, the desired treatment effect that we want to reach. So this study shows that given enough dose in the treatment target, we can really avoid VT episodes. What it does not yet answer is what the long-term toxicity implications are. Of course, the heart itself is also radiosensitive, which means also the healthy heart does have a reaction to radiation, and we need to minimize that as much as possible. So we want to try this now also clinically here at UMC Utrecht. We just started enrolling for the ProStar clinical trial. This is a really interesting experience because it combines information from radiation oncology, where I come from, with also cardiology and radiology, which are different research disciplines. So it's a lot of shared knowledge that goes into preparing and running this clinical trial. And this is on the, also with the background of the European Stop Storm initiative. So that's a big European network of hospitals which we lead here from Utrecht, which tries to collect the European experience for these patients to also learn and improve together. I think we can go one step further than we currently do in ProStar. We can do this MRI guided and we can adapt to it in real time. So cardiac MRI is a really established imaging modality used in cardiology, radiology, and it plays already a role in the pre-treatment phase of radiotherapy. So to estimate and plan the treatment delivery before the actual treatment day. With the MR-linac, we can bring the same type of technology actually to the treatment session. So we can do this during treatment and use this information to adapt the treatment plan. So to really precisely focus the radiation and tailor it to each heartbeat. So we explore here a technique which is called beam gating. It very simply means the beam is only turned on if the part of the ventricle that we target is in the right position. As you can imagine, the heart beats 60 times per minute or more. So we need to frequently turn the beam on and off again. We need to do this very precisely to deal with cardiac motion. So this is something we are currently developing here in Utrecht. In terms of cardiac imaging on the MR-linac, I can show you some very nice volunteer images we acquired earlier this year. This was the first time cardiac imaging was done on an MR-linac system. So this is still fairly new in the radiotherapy community, and you can see really the pristine image quality here and how it very, very nicely shows all the anatomical detail that we want to be aware of during treatment. This is acquired during a short breath hold to assist the image quality and to get these nice anatomical images. We can actually also get functional images, so we don't just know about the anatomy and the position, we also can learn about the function of the cardiac tissue. So that's what we call T1 and T2 mapping, and that gives us an indication of how healthy the tissue is and is potentially also usable for treatment plan adaptation. To really image in each heartbeat, we need real-time MRI, and that's an example shown here. So you see on the left-hand side the red box, which is following a part of the left ventricle. This is free breathing, so we have respiratory motion, we have cardiac motion. We are able, with post-processing, to tell the two components apart and to estimate and adapt to each of the types of motion individually. And that's something I want to show here. So we have a combined motion signal, of course. Patients are just free breathing, breathing easy. So they have cardiac and they have respiratory motion, which influences the position of the heart. We need to be able to tell those two types of motion apart in real time. And then we can deal with the respiratory motion using dynamic tracking, as shown in the first chapter. We can deal with the cardiac motion with beam gating, as shown in the second chapter of this lecture today. So I want to leave you with this impression. This is ongoing work. We are doing this as we speak, and we are still improving this. And of course, mimicking the journey that we went with tumor tracking. This is something we first did in silico. We're now doing it in phantoms. Next step is actually then the proof that it also works in patients. So to summarize, with the Unity MR-linac, we have the unique ability to see motion at a frequency which makes it possible to adapt the treatment to each heartbeat. So that's what I'm working on. Dynamic tracking, dynamic beam gating, and it's really, I think, a fascinating area of research because it opens up a lot of possibilities, not just for cancer treatments, but also for cardiac arrhythmia treatments. And both of these are huge societal needs at the moment, and will continue to be huge societal needs in the coming years. Thank you for your attention.
Thank you, Martin. Very nice and intriguing lecture. And it's very interesting to see how you're standing only at the beginning of the potential of these type of non-invasive therapies, where imaging and therapy come together. I also am very intrigued by the fact the central role of imaging and of course exact sciences. You're being a physicist, that's of course you're quite key to the development of this with a whole group of people. I think you can be proud of this research. We are proud of you, and to honor that, I would like to toast with you. So, congrats with your appointment, and jing jing.
Cheers.